details of the ionisation process aren't important. The essential point is that in each case, starting with one primary electron, we ended up with two. These processes can be repeated endlessly, so that one electron can produce an avalanche of electrons. During this sort of avalanche, there's an overall charge separation, with the positive ion moving in the direction of the field lines and the electrons moving the opposite way. So, as well as the external electric field, these moving centres of charge produce another field, known as a space charge field, and that acts in the opposite direction to the external field. There are lots of factors that affect the way the avalanches progress and the space charge develop. Factors like the shape of the electrodes, the gas pressure, and the composition of the gas. One possibility is that the avalanche can continue to grow as a thin channel of ions and electrons, what's called a streamer. Here, a streamer is beginning to grow from a negatively charged point towards a positively charged plate. When it reaches the bottom plate, there's a pulse of both heat and light. This can be explained if we think of the streamer as a conducting channel carrying the potential of the negative electrode. This means that the electric field at the tip of the streamer is very high, so more ionisation can take place and the streamer grows still further. Eventually, it bridges the gap between the electrodes, providing a high conductivity link.
So much for a gas. What about the breakdown involved in lightning? Well, breakdown, as you've seen, always involves accelerating charges, and it's very easy to detect accelerating charges. They emit radio waves. You've probably heard the radio waves earlier coming from the sparks in the Van de Graaff demonstration. They interfered with the electronic circuitry in the sound and produced a sort of thumping noise. Well, we can turn that idea to our advantage. We can look at the radio waves produced from within a thundercloud and use them to locate the accelerating charges, the dominant sources of electrical breakdown. That's what's happening on this film. In effect, this is a radio telescope view of a thundercloud. The horizon's just above the bottom, and the cloud covers about the top half of the frame. Every 2.5 microseconds, the dot displays the direction of the dominant radio source. Now watch carefully. There. The dot danced down to the ground and back, a lightning stroke, and again the dot moves up and down. Who says that lightning doesn't strike twice? Now obviously, the breakdown involved in lightning is very complicated. There's no obvious pattern to the radio source's movement. But with measurements being made every 2.5 microseconds, one thing is clear. The whole process is over very, very quickly. But if we could slow it down, this is what we think we'd see. You may be thinking that doesn't much look like a lightning stroke. You'd be right. What we've done is we've spread the various stages out horizontally so as to be able to distinguish between them. The lightning makes its first appearance as a faint luminous track below the cloud, and that jumps down towards the ground in steps. They're usually about 50 meters long. After each step, the leader stroke, that's what we call it, fades away, and then it glows again in the next step. After 20 milliseconds or so, the leader stroke reaches the ground, and then there's a violently bright return stroke. That's over in just a few microseconds, but the current during the return stroke is enormous, perhaps 10,000 amps. And this return stroke heats the air and produces the shock wave that we know as thunder. This whole process, the leader and the return stroke, leader, return stroke, can be repeated several times in a single flash, and that's why we often see lightning flickering. Now, you may be thinking that this description I've given you of lightning is very similar to Sheila's description of a streamer. You'd be right. We now believe that at the microscopic level, they are very similar. Unfortunately, trying to scale up a laboratory streamer computationally to something like a lightning flash is very difficult, and we can't really pretend that we understand every detail of the conduction process. But the description we now have can tell us how to avoid lightning. Think what happens just before the leader stroke reaches the ground. Then, the electric field between the bottom of the leader and the ground is very strong, so strong that there's a large charge concentration induced on any pointed object such as a steeple. Because of the field enhancement, an upward directed streamer can start from such a point, and the return stroke is going to pass along the path of the streamer. Here you can see how the return stroke has chosen the central streamer of a group of 3. In this case, the 2 abortive streamers, about 10 meters on either side of the bright return stroke, don't have an obvious point of origin, but perhaps they started from the tip of a blade of grass or a piece of rock. If the point is prominent, as is the case with this chimney, it can divert the lightning. You can see the sharp kink in the return stroke at the point where the upward streamer has met the leader, and in effect, it's drawn the lightning stroke towards the chimney. So the secret of avoiding lightning is to make sure that upward directed streamers don't originate on you. If you're below a thundercloud, make sure you don't provide a point where field enhancement can cause breakdown.